Soaps and detergents are part of our daily life. But do you know that the precursor for soaps are sodium hydroxide? Sodium hydroxide is such a compound which is prepared through chloralkali process, which is an electrolytic process. So how does this process occurs? What makes these so-called electrolytes so conductive to electricity? In this video, we will discuss the conductance of electrolytic solution before understanding about electrolysis and electrolytic cells. Before discussing about conductance of electrolytic solutions, you need to familiarize with some terms. These are electrical resistance, resistivity, conductance and conductivity. First, we will discuss electrical resistance. Resistance is simply the opposition to the passage of electrical current. From physics, you might already know that the unit of resistance is ohm. The electrical resistance of any object is directly proportional to length and inversely proportional to the area of the object. The proportionality constant is denoted by the Greek letter rho. It is called specific resistance or resistivity. If we use an object of length 1 meter and area 1 meter square, the resistance will be equal to resistivity. Or we can say that resistivity is the resistance of unit volume of an object. Conductance is simply the inverse of resistance. So conductance equal to G equal to 1 by R or equal to A by rho L. So the unit of conductance is ohm inverse or mho. Generally, Siemens is used as the unit of conductance. However, conductivity is the inverse of resistivity. That is, conductivity kappa is equal to 1 by rho. Substituting this in the equation for conductance G equal to kappa A by L, kappa will be equal to G L by A. The SI unit of conductivity is Siemens meter inverse. Like for resistance and resistivity, for an object of 1 meter length and 1 meter square cross-sectional area, the conductivity will be equal to conductance. Or simply, conductivity is the conductance of unit volume of an object. So what exactly determines the conductivity of a material? The magnitude of conductivity varies a great deal and depends on the nature of the material as well as temperature and pressure. Mainly depending on the magnitude of conductivity, materials are classified into conductors, insulators and semiconductors. Most of the metals and their alloys are examples of conductors, and non-metals such as carbon black and graphite are also conductors. Insulators like glass, ceramics and plastics have zero conductivity. Substances like silicon, doped silicon and gallium arsenide have conductivity between that of insulators and conductors and are examples of semiconductors. And there is another class of materials with zero resistance or infinite conductivity. Such materials are called superconductors. Nowadays, certain ceramic materials and mixed oxides are known to exhibit superconductivity at temperature as high as 150 Kelvin. Earlier, only metal and alloys at very low temperature of 0 to 15 Kelvin were known to show superconductivity. What you are seeing here is a magnet levitating above a high temperature superconductor cooled by liquid nitrogen. Conductance through metals is called metallic or electronic conductance. This is due to the movement of electrons. The electronic conductance depends on three things: nature and structure of metal, valence electrons per atom, and temperature. One thing to note here is that it decreases with increase in temperature. We know water is a conducting material, even though it is weaker. This is due to the presence of hydrogen and hydroxyl ions. However, when same salt is dissolved in water, the conductance increases due to the presence of sodium and chloride ions in the aqueous solution. This conductance due to the movement of ions is called ionic conductance or electrolytic conductance. The conductivity of electrolytic solutions depends on the nature and concentration of electrolyte as well as the size of the ions produced and their solvation. Also, conductivity changes with the nature of the solvent and its viscosity. Unlike metallic conductance, there are two major differences in electrolytic conductance. Firstly, it increases with increase in temperature, and secondly, passing the direct current through the ionic solution changes the composition of the solution. Unlike metallic conductors, we cannot connect an electrolyte solution to a Wheatstone bridge. So to calculate the conductivity of electrolytic solutions, we use a conductivity cell. It contains two platinum electrodes coated with platinum black separated by a distance L with a cross-sectional area A. Here the source of power is an alternating current. Then the solution separating the two electrodes have a resistance R will be equal to rho L by A. The cell constant G star depends on the distance between the electrodes and the cross-sectional area A, that is, G star will be equal to L by A. Measuring length and area is difficult and unreliable, so cell constant calculation is a bit difficult. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations and at different temperatures. The cell constant G star is then given by the equation G star will be equal to L by A, which is equal to R kappa, where kappa is a conductivity. Once we measure the cell constant, we can use it to measure resistance or conductivity. The resistance of the ionic solution is calculated by connecting it to a Wheatstone bridge as shown here. It consists of two resistance R3 and R4, a variable resistance R1, and the conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by an oscillator O, which is a source of AC power in the audio frequency range 550 to 5000 cycles per second. P is a suitable detector. A headphone or other electronic device is used for this purpose, and the bridge is balanced when no current passes through the detector. Under these conditions, the resistance of the conductivity cell R2 is given by R1 R4 divided by R3. Now that the conductance and resistance are known, we can find conductivity kappa is equal to cell constant G star divided by R. Even if you measure the conductivity of different electrolytes in the same solvent and at a given temperature, there will be difference. This might be due to charge and size of the ions in which they dissociate, the concentration of ions, or ease with which the ions move under a potential gradient. It is therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, denoted by the symbol lambda m. Molar conductivity is related to the conductivity of the solution, as lambda m is equal to conductivity kappa divided by concentration C. Here, unit of kappa is Siemens meter inverse and that of C is moles per meter cube. So the unit of lambda m is Siemens meter square mole inverse. We already know that 1 mole per meter cube is equal to 1000 liter per meter cube into molarity, that is moles per liter. Then we can rewrite the above equation as lambda m equal to kappa into 1000 divided by molarity. Let us apply this concept to solve this question. The conductivity of 0.2 molar solution of KCl at 298 Kelvin is 0.0248 Siemens centimeter inverse. Calculate its molar conductivity. Given that conductivity kappa is 0.0248 Siemens centimeter inverse and molarity is 0.20 molar, we know that the expression for molar conductivity is lambda m is equal to kappa in 1000 divided by molarity. Substituting the values, we will get molar conductivity as 124 Siemens centimeter square mole inverse. Both molar conductivity and conductivity change with concentration. If you recall, the conductivity is the conductance of unit volume of solution kept between electrodes of unit cross section and unit length in between. And molar conductivity is the conductance of a solution of volume V containing 1 mole of electrolyte. That is, conductance G is equal to kappa L by A, which is equal to kappa if length is equal to 1 meter and area is equal to 1 meter square. Then lambda m we can write as kappa into V. Since molar conductivity is directly related to volume, this means that molar conductivity increases with decrease in concentration or increase in volume. So, molar conductivity increases with decrease in concentration because the volume containing 1 mole of electrolyte increases. Or in other words, the ions of electrolyte have more space to move around, thus increasing the molar conductivity of the solution. However, conductivity decreases with increase in volume as the number of ions within the unit volume of solution decreases upon dilution. Physically, it means that at a given concentration, lambda m can be defined as the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches to 0, the molar conductivity is known as limiting molar conductivity and is represented by the symbol lambda 0m. This plot shows that change in molar conductivity concentration for a strong electrolyte KCl and a weak electrolyte CH3COOH. Molar conductivity vary differently for strong electrolytes and weak electrolytes. For strong electrolytes, molar conductivity slowly increases with dilution and can be represented by the equation lambda m is equal to lambda m0 minus a root c. This is a straight line with a slope is equal to minus a and intercept lambda m0. The value of the constant a for a given solvent at a temperature depends on the type of electrolyte, that is, the charges on the cation and anion produced by the dissociation of the electrolyte in the solution. For example, magnesium sulfate and copper sulfate have the same A values since they both are the examples of 2,2 type of electrolyte, means the ions have the same charges in both the compounds. German scientist Friedrich Kohlrausch observed that the difference in the limiting molar conductivities of electrolytes of the type NaX and Kx remains constant. That means lambda m0 of KCl minus lambda m0 of NaCl will be equal to lambda m0 of Kbr minus lambda m0 of NaBr, which is also equal to lambda m0 Ki minus lambda m0 Nai, which is equal to 23.4 Siemens centimeter square mole inverse. He also observed that the lambda m0 of NaBr minus lambda m0 of NaCl is equal to lambda m0 Kbr minus lambda m0 KCl, which is equal to 1.8 Siemens centimeter square mole inverse. Based on these findings, Kohlrausch created the law of independent migration of ions. It states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Generally, it is represented by the equation lambda m0 is equal to nu plus lambda 0 plus nu minus lambda 0 minus, where nu plus and nu minus are the number of cations and anions respectively, and lambda 0 plus and lambda 0 minus are the limiting molar conductivities of cation and anion respectively. Now, using this concept, find the limiting molar conductivity of magnesium sulfate. It is given that the limiting molar conductivities of magnesium ion and sulfate ions are 106 and 160 Siemens centimeter square mole inverse respectively. Now, if you look here, by substituting the values of the limiting molar conductivities of magnesium ion and sulfate ion in the equation lambda 0 equal to nu plus lambda 0 plus nu minus lambda 0 minus, you will get the final answer as 266 Siemens centimeter square mole inverse. Comparing to the strong electrolytes, molar conductivities of weak electrolytes increases upon dilution. This is due to the increase in degree of dissociation upon dilution. Consequently, the number of ions in total volume of solution that contains 1 mole of electrolyte will also increases. In such cases, lambda m increases steeply on dilution, especially near lower concentration, as you can see in this graph. Therefore, the limiting molar conductivity lambda 0m cannot be obtained by extrapolation of lambda m to 0 concentration. At infinite dilution, that means when the concentration C approaches 0, electrolyte dissociates completely, or we can say that degree of dissociation alpha will be equal to 1. But at such low concentration, the conductivity of the solution is so low that it cannot be measured accurately. So, the limiting molar conductivities of weak electrolytes are calculated by using the Kohlrausch's law of independent migration of ions. And degree of dissociation can be found by the equation alpha is equal to lambda m divided by lambda 0m. Using Kohlrausch's law of independent migration of ions, it is possible to calculate lambda m0 for any electrolyte from the lambda 0 of individual ions. It can also be used for the determination of the dissociation constant of weak electrolytes once we know the value of lambda m0 and lambda m at a concentration C by the equation Ka is equal to C lambda m square divided by lambda 0 m square into lambda 0 m minus lambda m. Based on the concepts we have discussed in this class, try to answer this question. Limiting molar conductivities of NaCl, HCl and sodium acetate are 126.4, 425.9 and 91 Siemens centimeter square mole inverse respectively. Using this, calculate the limiting molar conductivity lambda m0 for hydrogen acetate. Now, let us summarize what we have discussed so far.
Manorama Horizon. Learning made simple.